Hello, my name is Ayana Mateus, and today we are particularly interested in estimating the shape parameter of a shift log logistic distribution, also known as a three-parameter log logistic distribution. This is a joint work with Frederico Eire. We are both from Nova School of Science and Technology in Portugal. This presentation will be divided in 4 parts. In the first part, I will briefly introduce the three-log logistic distribution. Then I will speak about the estimator and the study, also presenting its asymptotic distribution. Finally, I will end the presentation providing some results based on a Monte Carlo simulation study to assess the finite sample performance of the estimators considered in this work. So, a random variable x follows a three-parameter log logistic or a shift log logistic distribution if its distribution function is given by this expression. The constants alpha, θ1 and θ2 are respectively the shape, location, and scale parameters. We use this notation whenever the random variable x has the distribution function in 1. We know that when we have a three-parameter log logistic distribution and consider the location parameter equal to 0 and scale parameter equal to 1, we obtain the standard log logistic distribution. This model is also known as a Pareto type 3 distribution. When we consider the same distribution with a location parameter equal to 0, we will obtain a two-parameter log logistic distribution. It is known that this model is a member of the burst type 12 family of distribution. So, what was the motivation of the work presented here today? We know that the log logistic is used in different fields of study, such as hydrology, economy, and survival analysis. Alzunala and Alzadar studied the best linear and base estimators for the location and scale parameters of the log logistic model with non-shape parameter. Although in real life situation, the value of the shape parameter is unknown. So we must estimate it. So to use the best linear and base estimators for the location and scale, we first need to estimate the shape parameter. Another result that is very important is that the log logistic is a member of the Pareto type distribution with tail index equal to with tail index alpha. So, several estimators for the heavy tail index alpha exist in the literature. The most popular estimator for this tail index alpha is the yield estimator. So, the estimator that we are going to use in this work is a modification of the yield estimator in order to make it both shift and scale invariant as follows. So, Alzuna and Alzada proposed the modified yield estimator for the shape estimator. So, the estimator for the shape for the shape estimator of the shift log distribution is given by this expression, where HK is the modified yield estimator. As already said, in order to make it both shift and scale invariant. We deduced its asymptotical distribution. So, under the validity of the second order condition and for intermediate sequence K, the asymptotic distribution identity holds, where Zk is an asymptotical standard normal random variable. The reduction of the bias is another topic that has deserved attention of the research community. So, in order to reduce the bias, we consider a bias correct version of the previous estimator, of this estimator, by multiplying it of a function of K. So, to access the finite sample performed of the two estimators considered in this work, we made a Monte Carlo simulation study with 2,000 samples of size 1,000, and we obtained estimates for the corrected yield estimator, for the modified yield estimator, the ones proposed by Alzuna and Alzader, and for the ones with the bias correct version. So we obtained simulated values for the mean value with this expression, for the median, also for the standard deviation, and for the root mean squared error. So let's see simulated results for all values of K. Here we consider a log logics parameter distribution with shape parameter equal to 0.5, and for the location and scale parameters equal to 1. So the results for the modified estimator are in dark, and for the bias correct version are in red. We can conclude that the new estimator that has a bias correct version has a smaller absolute bias than the modified yield estimator, but a higher standard deviation than the modified yield estimators. We can see that the choice of K involves a balance between bias and variance. Regarding the root mean square error, we can conclude the corrected bias version is more efficient than the modified yield estimator. We consider another log logics distribution with shape parameter equal to 1.5, location parameter equal to 0, and scale parameter equal to 1. And the results that we achieved are the same for the other log distribution that we consider. We can see again that the new estimator has a small absolute bias, but a slight higher standard deviation than the modified yield estimator. Again, regarding the root mean square error, we can see again that the corrected bias estimator version is more efficient than the modified yield estimator. Now we present simulated results for the optimal level of K. We consider here the optimal level of K, the value of K that produce the minimum root mean squared error. And here are the results for the two models considered in this study. For each model, the best value is presented in bold. What can we conclude? We can conclude that at optimal level, the mean value and the median are very close for the both models here considered. This result is expected since both emitters have an asymptotic normal distribution. We know that Alzona and Alzadra proposed the use of the modified yield estimators with a level K about 10% of the sample size. Although with these results, we think it's sensible to use the correct Bayer version of the estimator. But with the level of K equal to 30% of the sample size, since here we have here the optimal sample fraction, about 40% of the sample size, and here again. Okay, but the choice of K should be addressed in future research work. So here we have the main conclusions, but that I already spoke. And thank you for your attention.